applications of SAR data in agriculture, forestry, and other industries, along with biogeographical parameter estimation and planning studies. We are delighted to have you here. Sir, I now invite you to deliver the session.
ఇలా చూడగల దాంట్లో ఇది ఇలా కనిపిస్తుంది. ఇది బ్లర్ వచ్చింది అనుకో, ముందటి కొంచెం తిప్పుకో లైట్ గా కొంచెం. జూమ్ చేయి, జూమ్ చేయి. ఉందా? ఫుల్ ఉందా? ఫుల్ జూమ్ ఫుల్ చేయి. ఆమెకి ఇక్కడ టాప్ తీ ఒకటి. మస్తు ఇస్తుంది నీకు తెలుసు. నువ్వే తీసుడు బెటర్ అన్నట్టు. ఓకేనా?
Good morning, everyone. Good morning. I want to get more like interactive. You can actually stop on any slide, like the session and question and answer there. So today I'll be talking about collaborating start data processing in this application is in agriculture. So since I have two sessions, afternoon and now and afternoon, so mostly the data processing session I will be having in afternoon, so I'm very busy learning how to handle the current modern SAR data sets, the nicer and larger session. In this presentation, I will be talking about a brief. Can you go to the... So here's kind of the outline of the current session. So I will just give a brief background of current modern SAR missions and data availability and the processing tools available, and a quick introduction of colorimetric SAR. So, and a few descriptors or parameters which you can extract from the colorimetric SAR and how you can use it for agricultural process, and And two kind of examples using colorimetric SAR information, crop growth monitoring, and biophysical parameter estimation, and also the other one, a soil moisture estimation. Yeah. Coming to the current landscape of modern SAR missions. Yeah, why I kept it as modern SAR missions? Because as you know, the first SAR mission is 1970, it's been more than 40 years. Back then, the data volumes compared to now will be very low. To give a perspective, the current NISA data, I think generating more than 40 terabits of data per day. Okay, I'm not wrong. And the Sentinel generation, the Sentinel constellation is generating 1 terabytes per day or so. So now we actually have more data than we can ever analyze by classic ways or computing techniques. So, and also most of the data is nowadays hosted in the cloud. So we have to upgrade our skills, whether it is same exact algorithm of SAR processing, but now in a different kind of landscape. And today I'll be mostly focusing on NISAR and Biomass mission because Sentinel-1 almost is 10 years, more than 10 years been now, so you can find a lot of tutorials or information on this. A couple of thousands of research articles published in Sentinel-1 data. And since these two missions are currently a pre-calibration stage, not most of you might not be aware of how the data looks like or how to handle the data even because not a lot of information out there. So I thought that would be more useful for you to focus on. And we do have EOS-04 from ISRO currently operating. It is, I think, launched 2 years ago, and we have different modes of operation as well. And there is another open data from Jackson. So, coming to the data availability and the tools for processing these choose data sets. So, because of, thanks to the Indian Space Policy 2023 years ago, which is introduced 3 years ago, all the ISRO archive is made open to the public, courses than 5 meter resolution. So now you can get both optical and the current ISR data, which NASA and also the European Space Agency have been also kind of focused into more towards open science and open development and framework. And as I mentioned before, most of the data is nowadays pushing to the cloud because the scale of the data becoming from terabytes to now it is in a petabyte scale. It's not realistically possible to process on any local machine if you have a huge data set. And coming to the polarimetric tools or the processing tools which are openly available, mostly I talk about open source tools. The first one is IEEE, which is developed from NASA JPL. For a matter of fact, the current NISA data is being processed. Main processing backend is being done with IEEE. We have SNAP from European Space Agency, which is Sentinel application platform, which supports both optical and SAR data sets. But again, if you have a diversity of functionalities, then there is a trade-off that you have in-depth, large varieties of functions for any specific application type. And we have also Pro from US Reference, which has, I would say, I've learned my colorimetric processing from Pulsar Pro, and most of it's been there for more than 2 decades. But now we have adapted to the cloud because it was written in classic C code back in 22 years ago. And we have Midas. Most of you may not have been familiar with it. This is from ISRO. So ISRO's in-house SAR processing tool, which is openly available but not open source. It's free but not open source. And Pulsar tools, today I will be talking about this, which I've been working on since like 6 years. In the afternoon session, we will see more details about this. So the data sets availability, the NISA data available through two, one is NASA distribution and the ISRO distribution side, one is Puniti, as yesterday's Professor Srinivasrao mentioned about Puniti, so we will be expecting the SBAN data. The SBAN data is available through 2 services, one is ASF archive and data. Of course, if you are interested in using any cloud-based kind of resources, you have an S3 bucket, you can directly access that directly read instead of downloading. And for biomass data, you can get the data from ESA's map explorer. So currently there are different types of products we will talk about in the afternoon data processing section. With a brief info of the current landscape of open data sets available, let's see what its poles are, the polarimetrics are. Before jumping into that, a brief overview of what is a wave polarization. So you might have seen this kind of graphic in most of your polarization class, where you have a classic orthogonal component of electric and magnetic field in the EM wave, which is propagating perpendicular to their axis. So for all practical purposes, we mostly consider the electric field component of it, and the orientation of the electric field component in the EM wave actually is called the polarization. That's what is named specific. So, and again, this is, I would say, there's a famous question called what is up in space? Which direction is up, which direction is down, or which direction is horizontal in space? Because it is always kind of with reference to something. There's no up in the space or the down. So all this with reference to our Earth surface, because we are using SAR for Earth observation. So the orientation of the electric field we consider for the, with respect to the surface of the planet. So if it is flat, parallel to the Earth surface, which is horizontal polarization, and then vertical, we have an incline, we call it as bilateral mode. And we have what there is 90 degree phase difference between H and P, which is called a circular polarization. Next. And more geometrically or mathematical framework, we can actually represent all of those possible polarization states in a polarization ellipse. If you can recollect from yesterday's post lecture, you might have seen this. So there are like two different two parameters which describe this ellipse. One is this orientation of the ellipse, and the other one is this ellipticity we call. So for a, let us say the tau ellipticity, if it is 45 degrees, it would be a perfect circle, so it is a circular polarization. And if it is zero, then you class it as a single line. It's a linear polarization. And based on orientation, if the phi is zero, it is horizontally oriented. If phi is 90 degrees, it's vertical component. So you can derive this. So this is orientation angle and electricity angle, and the actual amplitude is the resultant of both x and y component of electric field. So coming to the polarimetrics, so we can start with what polarimetrics are data. I think again you might have seen this matrix form representation of SAR data in yesterday's lecture. So in one data format, we'll have four different channels. So we transmit horizontal and receive both horizontal and vertical. And same we do with the vertical transmit and receive both horizontal and vertical. So in a vectorized form, matrix form, we represent in this way. So if you have anyone work with the NISAR, just label that what kind of data is packed into what kind of data products. So you can actually from this single loop complex data, you can represent a second order average matrices from S2 matrix. This is essentially to extract a more meaningful or physically meaningful information from the polarimetric data set. So one is the lexicographic feature vector. I mean, it is simple that you just arrange these four channels in a kind of a more named fashion that you will have a four cross one vector. Then you multiply with a complex conjugate transpose, then you get a 4 cross 4 matrix, which is called a covariant matrix. And similarly, you can do with another basis, polybasis, which is an arithmetic combination of those four different channels. And you do the exact similar way of what covariance is called a covariance matrix. So, important takeaway is all of our NISAR or level 1 products mostly packed into S2. So, RSLCs or level 2 GSLCs provide you these matrix elements and the covariance nature, mostly they will give you these diagonal elements of this matrix. In general, a full covariance matrix will also provide this, but in general, currently the NISAR is providing this for full polarimetric one. We do have, so yeah, here is a quick graphic or the map of how a full polarimetric SAR data looks like. So this is biomass P-band data acquired over India. So this is the openly available data as of now, since last 4 months. There are currently 16 spots. Yeah, you can see some kind of RFI or kind of weird artifacts over western part of India. That's because of radio frequency interference. And on the right part, actually you can see the towards the east coast and the northeastern part of it. You can actually see different color combinations. Again, these combinations are similar to your optical first color composites. Like we have a standard first color composite in optical. We have a similar one of the widely used first color composite for the quad pole, where we use red as the difference between H minus PV, blue as mostly these are again represents the surface bound, double bound, and volume scattering if you're familiar with those terms. And again, we call it as poly basis because it is actually coming from the previous 4D poly basis vector. The three elements are three colors. And here you can see this is the Godavari Delta region, this is Sundarban, and this is Brahmaputra's floodplain. Coming to the another polarimetric data mode, which is we have two different modes. Instead of 4 channels, you can actually also get 2 channels. The advantage being able to cover wider swath, twice the amount of swath we can cover with dual pole compared to the full pole. So again, either it can be HV or VP or VH, but currently NICER is providing the global mode is in HHHV, but Sentinel it's VV and VH. So this is your NICER globally available RSS and GSSC elements, and the covariance matrix of this in the similar fashion we can get the covariance nature of it by multiplying with complex conjugate transpose of the SX1. So these are the direct elements are always the real, which is floor 32 or real numbers, and diagonals are mostly the complex numbers. Similarly, you can have another polarimetric mode, compact polarimetric mode, where you transmit a circular polarization and receive orthogonal linear polarizations, or H or B, we call it CH or CB. The C can be either again right circular or left circular based on your anti-clockwise direction. So here is another map of NICER dual polarimetric SAR data acquired over India. So this is just been generated using a cheaper product. I think there's 500 gigs of data downloaded and processed just to see how well the data is doing. Again, the caution is that both NICER and bioimagination are in recalibrations here. They may see a lot of this artifacts here, some RFI, and also some very banding across the range and the swaths. But despite that, you can actually see final details. Again, I have here forest, Godavari Delta, and also the Kutch in Gujarat. You can see the polarimetry mostly deals with more than one polarimetric channels, where you will have more information compared to one single channel. So where you can the polarization of the wave kind of changes the scattering, the scattered wave polarization, the polarization of the scattered energy or EM wave is kind of directly dependent on intrinsic properties of physical properties of your land surface or land features. So when you have one polarization versus two polarizations, so you can get two different kind of informations in two polarization because of the orientation of the electric field. And if you have 4, so even better. So the same sense that you will get in investigative terminology, you will have more features or more dimensions to your data. Yes. So coming to the pulsar, how do we kind of categorize this? It's because we have 4 complex numbers in quad pole and 2 complex numbers in dual pole. So we can extract some physically meaningful parameters or what you call descriptors or polarimetric descriptors or polarimetric parameters, which can be directly related to the physical scattering mechanism in the kind of on the land. So today I'm going to kind of focusing on the 2 different concepts: degree of polarization, scattering entropies, what is the scattering type parameter, and what are those decomposed powers of polarimetric decomposition gates. And a quick introduction of it. So each one is one slide, and I'll show you the formula and how the actual data looks like. Yeah, please. So coming to the degree of polarization. So it is a kind of a measure of fraction of polarization structure present in a scattered, backscattered energy. Because backscattered energy we can measure both amplitude and phase. and the polarization of the state. So in general, this is the kind of formula called Barakas degree of polarization. So where this is your covariance matrix or coherence matrix, and the N is in terms of dual pole, it is 2 cross 2 covariance matrix, so N is 2. And in full pole case, it can be 3 or 4, because based on you are using a covariance of 3 by 3 or a 4 by 4 matrix. So again, understand that this the matrix nature of it is for each and every pixel. It's not the same base. So for each and every pixel, you will have an entire 3 cross 3 matrix for quad data. So here is the first, what do you call it? First openly released nicer data over Madhya Pradesh. So the degree of polarization, if you see, the higher degree of polarization usually we observe on like mostly where your bare soils and so on, like rough but bare soils, and low degree of polarization mostly we observe on vegetation and mostly water surfaces where you lose the polarization structure because of multiple bounces or kind of forward slide. Polarization scattering and roll. Scattering and roll. There are like two ways of defining entropy in polar pulsar. One is a classic entropy, which comes from thermodynamics, the randomness, and the system. And the second one comes from the information theory, which is Shannon entropy, which kind of defines the entropy in two different components. One is intensity based on what is the return energy in both different polarization channels. And the second one is polarization based entropy, polarization fraction of it, which talks about the relative polarization nature of different channels. So what you can see here, first the exact state, dual pole, nice to see. So the first one is the intensity based entropy, and the second one is polarization based. Can you find any kind of difference in both? Sorry? Angle. Which angle? I think it's exactly the same. The angle I'm talking about, let's say, the radiometry of it. Radiometry in the sense, the color grading. I mean, if you are closely observed, there is this color banding in polarization entropy, but which is not there in amplitude-based entropy. Yesterday, I was discussing the same with Paul. So, if you decompose that entropy into two components, this only based on radiometry, only deals with the amount of energy and independent of the polarization nature of the wave. And if you see the polarization nature of the wave, compute the polarization randomness, then you can see that there is some mismatch between those two channels polarization because of the kind of now recalibration stage of the data. I kind of searched through it, and a kind of vague, what do you call explanation for this banding only in polarization is the cross pole of nice currently the HV channel is not yet kind of well calibrated or not behaving as expected or ideal. So that is what kind of producing this swath-wise radiometric banding, which you might have seen in the previous slides also in the swath. So that is mostly because of polarization kind of calibration, not the intensity or energy base. So this is one of those, what do you call this, fine physical parameters we can kind of look either to debug the data, assess the data quality, or use it for the same applications for any ecosystem applications like agriculture, forestry, etc. And we have another coming to the, from dual pole to a quad pole nature of it. We have another similar as I mentioned. This entropy formulation comes from a thermodynamics based system. So more random the scattering, and it deals with the eigenvalues of the 3 cross 3 matrix which you have seen for the covariance of covariance matrix. And there is another parameter called scattering type parameter. The scattering type parameter essentially used to determine or kind of explain the dominant scattering mechanism for any single pixel. So let us say if we have a star pixel and whether the pixel, whatever the target or the features inside the pixel are behaving towards more like a surface or more like an upon or volumes. Usually it is expressed in angles. So I've given this colors, and also this is from We also call it cloud quality of decomposition. So this is mostly eigen-based decomposition to verify or understand the scattering behavior of a specific pixel. So here what we see is on the x-axis increase in entropy. The more higher the entropy, the more random the scattering. And the y-axis we have scattering type parameter. So the color-coded one, the bluish is mostly the surface scattering, and the greenish one is mostly volume or random scattering, and the reddish one is we call even bond scattering or double bond scattering. When you have two orthogonal surfaces like buildings or tall trees, so it will take two bounces, we call it even bonds, or surface mostly have single bonds and come back to the sensor, so it's called odd bonds. And in vegetation, so kind of in random media, it go through multiple paths and the resultant will be coming out, multiple scattering or volume scattering. So if you apply the same clustering algorithm for actual original data, so this is a UAV star full polarimetric L-band data acquired over agricultural fields in Canada. So giving the same framework, if you want to kind of cluster or using classification or cluster a full polarimetric or quad polarimetric data. So this is again a poly RGB, which I have shown you before, different combinations of channels. And if you do directly a simple unsupervised kind of clustering based on each other, this is how those fields look like. So now you can see the bluish fields are mostly bare fields, and the reddish are mostly like the corn or oriented, like mostly the either plantation or corn. And the greenish are, I would say, high biomass, multiple scattered crops at that particular location at Alpine. Again, the scattering mechanism, the surface or double bonds or volume, strictly based on what wavelength you are using, what frequency you are using. Because a surface at a lower, shorter wavelength may not be a surface in a longer wavelength, then vice versa. So, and you can also plot the same clustering plot just to see how where the most of the data or most of the fields are, how they are actually behaving in terms of scattering properties. And the other concept is decomposition. Pulsar decomposition, you might have heard it a lot. So this is kind of a crude oversimplification of any decomposition. So the core idea is to have one observable, like a C3 or a T3 matrix, the covariance or covariance matrix. Now you have to represent that as a combination of different scattering mechanisms as a linear summation. So you can actually have n number of here, but most popularly we use a surface, double bond, and volume scattering. So now we have to split the same matrix as sum of these matrices. So that is kind of again it was problem as you can see because we have one observable versus three unknowns. So there are different mechanisms. You can actually fit some physical scattering models, or you can use an eigen-based approach, or you can use a degree of correlation-based approach to actually fit or split the same matrix into n different components. But if you do that, this is from one of the widely used Yamaguchi four-component decomposition. So from the same previous data, if you do that, as we have seen in the HR clustering as well. So the scene is mostly dominated by the bluish scale where you can see the reddish. So I have kept the color bar, but these are all normalized from 0 to 1. So 1 is highest, and the reddish color is 1, and bluish one is towards 0. You see less even bounds only where the fields are, let us say, mostly even bounds happens when you have in agricultural fields, when you have row-wise structure and also the strong high dielectric crops or bigger crops, because we are talking about L-band. So what happens exactly? The gaps provide a path to penetrate through the canopy and hit the crop surface or standing foliage and return back. And one of the interesting observation, you can say, from double bonds, this would be the highest return energy among all these, because this will have less losses because it's just hitting the ground and the vertical target or direct surface and directly coming back to the sensor. Unlike the art bonds, which is kind of scattered all across the globe, and only the component which is reaching towards scattering towards your sensor will be reaching in surface, and volume anyways you will lose much of energy because of those multiple scattering of it. So that's been a kind of a brief introduction of polarimetrics are and widely used different mechanisms, how you can parameters or descriptors, how you can use and relate with any portfolio or component. And as I mentioned before, if you remember, the GPO product has only the two diagonal elements of it. So where you will have HH and HU. So these are like intensities. If you are familiar with tubular region, where you will have signal data in only two intensity channels, VV or VH. So in that case, the previous formulation of matrix-based approach cannot directly derive those. So we worked on that. I mean, those are called ground detected products. So even with those two channels, you can kind of derive pseudo parameters. So in the equivalent, let us say, an equivalent to a degree of correlation for the so-called purity parameter you can derive based on a single parameter, which is the co-pole cross correlation. And similarly, similar to the scattering type parameter which you have seen before in H alpha, you can actually derive a pseudo target calibration parameter which varies from 0 to 45 and pseudo entropy. So these are the parameters you can use it directly for growth monitoring or estimation of crop biophysical parameters. I will show you a case study which we have worked on. So to test these formulations whether they actually work to monitor the crop growth at different phenological stages or not. So we have selected a data set over Manitoba, which is part of soil moisture active passive campaign held in 2012 using UAV SAR data. So we have actually focused on two particular crops. One is canola and wheat. These are kind of widely grown in Canada. And one of another interesting feature why we chose this, one is the data availability, and the second one is the fields are like huge, like a kilometer by kilometer, so that you will have more homogeneous fields to prepare your algorithms or that could match most closely towards your theoretical formulations. Yes. So these pictures show different phenological stages from simple sowing or leaf formation till the mature with the different TOI. TOI is the day of the year. So usually we mention the entire 1 to 365 days in the crop calendars and the days. So these are the different phenological stages of canola from leaf formation towards the maturity, and the same for the wheat. So this is the maturity. So now we will see all these 6 different phenological stages, all those different polarimetric descriptors vary in terms of quantitatively and also qualitatively over species. Yeah, these are the data sets. We used the Sentinel-1 study was, I think, 5 years old. And yeah, these are the data sets. They have like 7 or 8 data sets to represent collectively all these 6 phenology stages. So these are kind of a spatial variation or a maps of those 3 different descriptors which I mentioned. So first one is the descriptor entropy. As you can see from left to right, the entropy is increasing. So the left is mostly based on delta, and as the crop matures or crop grows, more foliage accumulates more biomass, it shifts towards reddish color. And the same happens with it happens oppositely with degree of coloration, because degree of coloration or the coloration structure deteriorates as you have more and more scatters. And you can see the scattering type parameter, I would say less sensitive in related to these two, but it provides a kind of a different information compared to those two for further kind of clustering or any other applications I'm sure later. So yeah. So can you go back? I just want to focus on one at a time. So if you see this kind of more bare surface, and where you expect that your entropy is way lower and your degree of purity or degree of coloration will be too high towards the ideal case, because you are not, the surface is not a depolarizing one. And again, I have marked those different stages like leaf development till the maturity. As the crop grows, again you can also see the color scheme. The greenish, darker greenish is like it has more and more water. we call it as more higher the dielectric, overall effective dielectric of the crop foliage will be higher in greenish. And once the fruit development and drought stage is there, so again after drawing, once it towards the maturity, again the water content goes down. So where you can actually see that entropy going up, and also when the water content is going down, the entropy goes down. So this is how it is. Yeah. Next. So now you can see each and every stage. So the entropy goes down. We have the values theta, this is degree of purity, the entropy, sorry. The entropy goes up and the degree of purity actually goes down in each phenological stage. Yeah. Next. So now you can actually see once the entropy actually increased from for each phenological stage up to maturity, and after maturity you can see there is a drop because of decrease in overall water content in the wheat pods. Similarly, it is kind of a similar pattern we have seen in canola, but in canola it is kind of what we call the crop structure. We call the pods. Actually acts like those granule-oriented dipoles kind of structure, and there is this interesting phenomena also. Once the flowering to the pod development, after pod development, canola sheds all its leaves. So all you left with the base skeletons of pods, which you can actually see that transition from the fully grown foliage towards only pods, as in terms of entropy as well. You can quantify that. Yeah, from leaf development stage, elongation, inflorescence maintenance, and after this, you see all the leaves will be gone in the next stage. Next. Yeah, so it's only left with those dipole-like structures. That's why you can actually see a little bit drop in entropy here, and further drop because it becomes more towards the dry. So similarly, using these two as you have seen clustering, clustering, you can do the similar with the H and the theta, where with increasing entropy, the more the foliage, the more the scattering is, goes towards the higher entropy, and space foliage mostly sits here. So if you plot the exact clusters from the same data for each phenology stage. So yeah, these are the kind of clustering maps where you can see those pinkish or magenta towards the base oil versus heavily grown towards a cyan color towards this more random scattering. Yes, now you can actually see the cluster moves towards each kind of different stage. It moves towards the higher entropy. If a cluster mostly falls between two, it kind of means that not the non-uniformity inside whatever your observation, some kind of plants or fields may not be exactly in the same phenology stage as they are in the other. Similar one you can plot for the canola. So you can again see the movement of the entire cluster towards the left to the right. And again coming back once the vegetation water content goes down. Yes, you can actually see the previous one. Yes. So here you can see once the water content is down from here to here, the cluster is actually moving back because of low dielectric nature of the crop foliage. Yes. Next one. So these are like descriptors in a way of monitoring this. If you want to kind of quantify, like I say, some kind of index, or if you want to extract the vegetation water and the biomass or something, we need more quantitative approach or an index-based one single parameter to kind of do that. We have done that as well. We call it as dual colorimetric radar vegetation index for GRT data, where we use the exact same convention, but Q is the cross-pole ratio, and we can express this PMSD as this. So it varies from 0 to 1, having exactly the same uniform kind of explanation. So 0 is mostly towards the surface and 1 towards the fully grown individual crop. We have also conducted some simulation studies with already available volume scattering models and how it is kind of behaving compared to the already available radar vegetation index for dual colorimetric SAR data. I also have conducted some simulation study with the first order single order radiative transfer model. which consists of a soil, some rough surface, and randomly oriented discs. So, if you increase the soil vegetation moisture and also the soil moisture, so this is how the TPRAC actually behaves. If you increase the vegetation water content, it increases and stays almost the same with soil moisture. So after a certain combination of soil moisture and vegetation water content at seabed, so they are kind of interdependent. So the TPRA it essentially consists of information from both soil and vegetation when the crop is grown and soil moisture is high. So here are the quick maps from the same study area, Manitoba area. So as this is we have done for only one particular crop wheat. Again, you can see the DPRA is increasing towards from left to right. And if you plot the actual DPRA with plant variables like plant parameters, input parameters, plant area index, dry biomass or wet biomass, you can actually see the trend. The temporal trend is actually well matching with the physical parameters of the crop parameters. And you can also quickly do a correlation of the vegetation index and vegetation index and the crop biophysical parameters. You can see we've got a decent correlation. I would say that it's great because it's just a simple linear combination, just plotting your vegetation index versus the biophysical parameters. Because it's not always linear, by the way, so it's just a quick kind of checking how well it is correlating with the crop biophysical parameters and whether it's useful to even estimate this or not. So, I've done an exercise by plotting this, how this DPRST looks looks like over India using L band data. Again, as you can see, so these dark blobs here, whatever you see is mostly RFI. So, and also this banding, as I mentioned before, because of the, since it is recalibrated data. Despite that, if you actually plot some specific forest, the first one is Gir National Park in Gujarat, and the second one is Sindipal in Odisha, third one is Narmala in Telangana. So it's in both states. So as you can see, there is a very good kind of spatial consistency and also the contrast between the surrounding non-forest versus the forest region. Yeah, these are the Google Earth images. So which means there is some useful information you can extract using these indices and relate it to crop or forestry biophysical parameters. And yes, I've done the same thing over entire US. It's a joint mission. So, and you can see there are like a lot of more these dark green patches in the US because compared to India, US, we have more RFI in US. That's currently, I think, a challenge for the calibration efforts as well. Despite that, you can clearly see some of the places. This is north to west. There is I don't know, Goa rainforest or something. I couldn't pronounce it properly. Sorry for that. But yes, you can, if you see it, it's actually a lush green forest with a snow cap. Where you have a snow cap, you don't have a see, and the rest of the forest you can see much more greenish. And this is California Central Valley, where you have both mostly normal crops and also orchards. That's why you see much more greener patches. Mostly those are orchards like almonds and grapes, which are like row-based structures and a very strong double bonds kind of scattering. And the other one is Talladega National Forest. It's a forest region, and you can actually see forest versus non-forest region, the greenish shades of the DPRSC. So yes, code is available if you want to derive those descriptors for DPRSC, and even scan this. The beautiful descriptors are also kind of created a Google Earth Engine app. You can view it on your mobile for Sentinel-1 data anywhere on the globe. For all the data sets, you can download this. You can go through the code. If you find bugs, you can report to me. So you can contribute to it. So yeah. If you're done, then I can move to a soil moisture estimation from crop. Or do you need a soil bag? A quick bag so that if anyone missed that, so you can quickly take it away. Yeah. Now, so since agriculture deals with most the crop and also the soils, now let's move to the soil. So one of the widely used drop backscattering model or simulating a backscatter for a vegetated canopy is watercloud model, which assumes or kind of models the vegetation canopy as a randomly distributed cloud of water droplets. So which we can explain, we can kind of describe as the total backscatter, we can actually express as the sum of scattering from vegetation component, soil component, and the soil component again has to pass through the canopy twice. So you will have this derivation of canopy, so which you can express using 4 or 5 empirical parameters, incidence angle, and a vegetation descriptor to characterize the vegetation. So here what we have done is we have used the radar vegetation index which kind of proposed that we to compensate the vegetation, kind of separate the vegetation component and then estimate the soil moisture. So again, we have taken this Manitoba test site and also tested in Germany. We have used the UV and ESA data L10. This is the kind of brief, quick methodology I would say, kind of more detailed. But the first one is extract the vegetation descriptors to compensate for vegetation or quantify it. And the second step is how do you estimate the soil moisture using the descriptor and backscatter values. So these are the backscatter, the soil moisture maps derived from dual combination of HH and HV at L10. You can see some kind of incidence angle variation from left to right near the far edge. But despite that, if you see the quantitative, the qualitative thing, it actually follows the rainfall or the field measure pattern in HHHV and also in VB and VH. So what we found is, as most of the studies also reported, so we got a better accuracy in HH and HV. Luckily, we have nicer data in the same HH and HV. And these are some quantitative results, so the validation results for different crops. So the previous one is a map of spatially how consistent it is. So as you can see here, it kind of works for specific crops and not so well for a few crops. So it is kind of a way that most of these vegetation descriptors of indices in SAR and assumes that vegetation medium has randomly oriented dipoles or multiple scattering, but that assumption may not hold for, let us say, broadleaf crops or kind of tree birds and so on. So where you have such kind of vegetation structure, so these kind of vegetation indices find kind of limited use case in that kind of campus. And we've also done kind of study with simulated nicer data back 5 years ago, because we have used L10 data, but we want to test it on simulated nicer data as well. So since because of the SNR differences, we see it's more kind of grainy in nature. Despite that, the temporal trend and spatial consistency stayed the same between USR and the simulated nicer data. And the second approach we did is the change detection approach. So for the soil moisture, the first one is water cloud model, and the second one is change detection. So conceptually, the change detection algorithm works something like, so if you have a backscatter from dry surface versus if you have a backscatter from wet surface, the difference varies based on how much amount of vegetation you have. So the more the vegetation cover, the difference will be less. So it becomes more, the difference becomes insensitive to your soil moisture change rather than it is dominated by vegetation change. So here, what we do is to kind of compensate for that, we can have a vegetation index and find out what is the sensitivity, how it is behaving for a specific sensor and a specific tester. So we have kind of used the same change detection algorithm using DPRPLC over openly available soil moisture data. We have international soil moisture network, which is called IS7, where you can get the temporal data for the last 10-15 years over across the globe. So one of that is well-maintained Excel network, which consists of more than 40 stations, which will have every hourly soil moisture data. So here is kind of the plot. It's close to that theoretical plot shown before. So if you plot NDVA versus the backscatter change, so as the NDVA increases, so the change in the backscatter or the difference in backscatter because of soil moisture decreases, which you can see as similar trend, much more steeper if you plot the similar one with the DPRPC. So these are the soil moisture maps. For 4 years, we have kind of taken just to see or kind of eliminate if there are any differences between the rainfall patterns between the years and so on. So the bottom one is the wettest period and the top one is the driest period soil moisture match. Here you can also see the topography, topography influence also. So this is my kind of mostly a ridge line. So where you would expect that the rainwater stays less and the valley shows more soil moisture. So this is the quantitative one. We've separated that to two categories. One is the shrublands and the other one is the croplands. And we've compared these results with the NDVA-based vegetation compensation versus the DPRVSE-based vegetation correction. So these are the correlation plots and the temporal plot. As you can see, the first one is NDVI and the second one is DPRVSE. DPRVSE has like less, better accuracy it showed across even the temporal scales. With that, I think. Yes. No, 1.5 hours. So, yeah, if you have any questions. Sure. No questions? Yes, sir.
Thank you so much, sir, for a brief concept. So I have a few questions. Can you go back to the H alpha clustering?
Sure.
Back.
Yes. This one?
This one. So you are here. You have classified into 7 zones.
Yeah.
I can see that
9.
So yeah, it's 9.
Yes.
One zone is 3. So basically, the zones like it is uploaded. So anything that is coming in zone 3, non-feasible is
Not visible. Yes.
like, what are the kind of surfaces?
That's a very interesting question. If I want to repeat it for the others, why this zone 3, despite we have 9 zones, why this kind of grade up? Is that what your question is?
Yes.
Why this is not visible?
Yes.
Because, so if you see this, the entropy, this axis you have higher entropy, which means more multiple scattering. This is kind of mostly surface. Theoretically, it is kind of not, it's not possible to have a surface which is having completely depolarizing nature. Because it is towards like the higher entropy is like you are kind of always having less and less polarization structure inside. But in general, surfaces, even if you increase super rough surface, they still preserve some polarization nature of it by default because your phase sets are actually again you have if you model that as phase sets and yesterday's class I think was total. So those phase sets preserve the flat and plane wave approximation some polarization structure. So theoretically you do not get for a surface an entropy more than 0.9. So that is kind of that's why it became non-feasible. So yeah. Again, it's the mathematical framework based on the eigenvalues, limitations of the eigenspace. But physically, that's how you can understand.
You can you go next slide?
Yes.
Next. This one. Back.
The decomposition.
Yes.
Yes. This one. Yes.
Here you have categorized into double count, single count, and volume.
Yes.
And plus.
Yes.
So, what can be possible decomposition? Like, how many numbers?
How many numbers is a good question still in kind of research or huge debate. Because let us say, if you take these are called elementary scattering or canonical targets. So one can imagine that the wave comes, hits any surface, it just scatters, either forward or backward, depending upon the surface scattering. That is the first category. The second kind of is you have an orthogonal surface, it hits the surface, the second surface, go back. Two. And a multiple scattering is like you don't kind of have a definite or deterministic nature of how it is placing any path. So that is kind of completely random towards you. But in between these two, first one bounce, two bounces, and infinite number of bounces. But you have in between n number of bounces in categories. So how they actually model these bounces? Let us say you have this surface, you kind of orient it in different ways such that you will have a, let us say, 3 or 4 bounces and go back to your sensor. So depending on the nature of about the path which the wave traces, you can have n number of scattering, elementary scatterings, and you can it's again like a minimization problem. So these usually they do like, let's say you have a dipole, you keep one dipole, you model it, how it kind of gets this scattering matrix. You have perpendicular dipoles, inclined dipoles. So for each elementary target, you can do that. But the question is, how do you validate that in terms of field? So that is always a research question you can ponder. I think currently we have 7 components available based on these laboratory experiments and the mathematical framework rather than physical one. Most widely used is the helical component, the helix, the 4 component MOG decomposition. The helix mostly appears in urban kind of scattering where you have when it takes like 4 or 5 bounces and reaches the sensor, like in a helical structure. That is one of those 4. But beyond 4, it is difficult to find any physical properties. That's my opinion. Good question.
Thank you, sir.
Yeah.
One just last question.
Sure.
It will be a very silly question, still I'm asking.
It's not a silly question. It's always a research question.
Scattering entropy. You have explained about scattering entropy, but why you are calling it pure scattering?
Because with just 2 intensities, theoretically it is impossible to call it as entropy. So this kind of gives us similar kind of, because I would say for certain targets like reflection symmetry, like vegetation, it matches to the same entropy as before. But for kind of non-reflection symmetry, for urban or surface scattering, that will be very different from actual scattering, actual entropy definition. It won't match the entropy definition, so you cannot actually call it as entropy. Just kind of approximating entropy, but not entropy. Yes.
Thank you so much.
I think this simple analytics decomposing the primary measurements to get those.
Yeah, from the first 4 channels, you have to make those matrices.
So we should see that it has to have 4 steps.
It can have a number of steps. How do you fit these different matrices? Let's say you have 3 matrices, you have to express that as a sum of n matrices. So that can be, in general, that can have infinite possibilities. But we try to find one unique set which is physically meaningful.
Thank you.
Any other questions? I think if you have received the message, it would be great if you can download and keep some data set for the afternoon answer session. So that will be dealing with how to produce the results which I have produced here, because so that it will be more, I would say, more useful and practically relevant. So yeah, thank you.
Thank you, sir, for that insightful session on geoscience.